Hello, Mr. Schultz here as we dive into more statistics, specifically 8.4 normal distribution. So make sure you write your name and the period in the top left and right hand corner of your PDF. Make sure at the end of this lesson you do a little reflection. Do you still not get it? Or number 4, can you teach others? Now, the specific standard we're going to dive into today or tomorrow if you're watching two parts of this video is to use the mean and standard deviation of a data set to fit it to a normal distribution and to estimate population percentages. All right, let's skip the rest of that and go on to the next part. Something to get you to evaluate yourself is to understand the idea of explaining the lesson and trying to write a quick little sentence. So please, if you can, after you're done, write a quick sentence. What is the basic gist of this lesson? Now, before we go jump into any of the examples that we have, I want you to go over some vocabulary and concepts with me. So let's give you guys a break in 3, 2, 1. So when we have each outcome of a statistical experiment and the likelihood of it happening can be mapped out, this is what we call a probability distribution. So let's write that down. Probability distribution. So also remember that the outcome is the possible result of an experiment. Or, it's like, one of a single event. Whereas, let's write this down, the sample space is the set of all possible outcomes of a probability experiment. All right, so now we're getting into a little bit more review a little bit. I love this idea of discrete versus continuous data. Discrete random variable is finite, or in other words, it's countable. So 1, 2, 3, 4, we are counting. It is countable data. Even sometimes half, like one car full of people, half a car full of people, but within reason. As long as we have a particular number that we assign it. For example, you can have one car full of people come in and half a car. So if a car full of people is 4, half a car would be 2, and that is countable. You can have that. However, with continuous random variable data here, continuous random variable, it can take any value. So if it sounds weird, like, hey, 1.75 people came in today, that shouldn't happen. That's more discrete random variable. But if you pull down on a candy dispenser and you fill in like 1.44 pounds of candy, you can have that continuous data. The discrete random is going to be a specific counting number, countable. So here's a visual example of it. Sum of 2 dice. It's going to be from 2 to 12, and it's not connected. There's no numbers in between. It's going to be 2 through 12 counting numbers. Now the miles per gallon right here, yeah, like you could have 22.34 miles per gallon if you're driving. It's going to, be determined by your car and how you are driving it. Let's go on. So before we go on, we need to understand that the probability, so let's write this down. The probability of each event happening is less than, it must be between 0 and 1. So the probability of each event, each x. So if we go up here and we look at the x, each of these x's happening has to be between 0 and 1. Probability of each x. The other thing that we have to understand is we have to understand that, like the sum of all the probabilities is less than 1. Oh, no, it must equal 1. Sorry. So how much is underneath? This is like this example right here. How much of this curve is here? If we add up all the probabilities here, it'll equal 1. So what does this mean in the greater sense of this? This is 100%. And that's equal to, all, the sum of all probabilities. So if you look right here, if we add up all the sum of all these probabilities of rolling dice, it'd be 100%. Like the dice will land all of these if you add them up. It's 100% of happening. That's it. All right, let's go on. So we have to classify some random variables right here, okay, guys? So first up, 200-meter swim times. I want you to think about this. Before we put it in, I want you to think about it. Is it counting, or can you have some sort of like continuous information? Like, hey, it can be in between 2 and 3, or 2.5 and 3. It can be in between. Is that possible? Yes or no? So 200-meter swim times on a swim team, individual archery scores, the number of students in a classroom, the amount of water in a bottle. I'm going to pause the video. I want you to try to get this answer before I plug it in. It's a quick little check before, to see if you actually understand it. Here we go in 3, 2, 1. All right, so here's the reasoning behind this. Continuous for the swim times, because you could have like 4.236666. So data is in between. It's okay. Number of students in class, you can't have 3.5 people in your class. A person's a person. So it's either 3 or 4, not in between. Individual archery scores. So if you look on a target, each of the target area has a specific countable number, like 2, 1, 5. And you can't have like 2.5. That doesn't work like that. But the amount of water in a bottle, it's not going to be exact. You could have 3 ounces. You could have 2.5444 ounces left. It changes. Let's go on. So example 2, analyze a probability distribution. So, hey, look, basically what this is asking is, hey, we have all of this candy and they're going to win a prize. And we want to have a frequency table that shows the number of winning wrappers for each prize. And so we can construct a relative frequency table and graph this probability distribution. So first up, we have to create a relative frequency table. So here we go. Here is the frequency table, except I have the prize, I have the frequency, but I don't have the relative frequency. So what I'm going to do is I'm going to take the total number and I'm going to divide that into each of the number of times it happens, and it will give me a decimal or a fraction or percent. I'm going to put it as a decimal and I'll go on. go ahead and let's do the first one. So if I have 1250, and I'm going to divide by 4,000, I should get, I'm going to pause it, I'm going to fill it in 3, 2, 1. So I get, on my calculator, I get 0.3125. Now go ahead and you do the same thing and keep going through this list. I'm going to pause it and write it myself in 3, 2, 1. All right, guys. So if I have this information, I can now take this and I can actually, graph it. So I'm going to take this information, I'm going to graph it. Here's my relative frequency table here, and now I just need to graph it. So I have my X, which is the prize money, and I have my relative frequency, which will be my Y. So let's go on. So graph the probability distribution. Well, okay. So I'd probably go like this. I'd be like, all right, I have, and it's not going to look pretty, but that's okay. I have 5, I have 10, I have 20, 50, and then I have 100, 500, 500, and then what was the last one? Was it 1,000? No, it was 1,000 and 2,500. Now, this information is not connected, so it's going to be, going to be a bunch of bars. They're not going to be connected. So what I'd also want to do is I'd be like, all right, 0.1 is right here. And then I have 0.2, 0.3, and then up here I have 0.4. So, if I look at the data, I can actually graph this. So for $5, it was like just above 3.1 right here. So I'm going to put this right here. I'm going to be like, I'm going to have it down. Now 10 was, I do believe, 25. So halfway in between the 0.2 and the 0.3. And then 20 is just below that. Looks like that. The 50. And the 50 is at 0.15. So halfway in between those two. So I'm going to fill in the rest because you don't need to see me mutter to myself right here. So I'm going to pause it and then put it. So as you can tell, it's not as accurate. I should probably use a graphing paper with this, or graphing grid to actually make this more accurate. But here's just a general idea of, hey, here's my probability distribution. And if I add up all of these, what percent should I get? 100% or 1. So now let's go pull up Desmos and look at it. So this is what Desmos looks like right here. You can see that. Hey, look, this is if we had actually made it into a curve, it kind of looked like this little curve right here. But the problem is, I had to set up the graph how I wanted it. I have my x's, my y, x1, y1, these are my points. But what I had to do was I had to make my x-axis from -100, so it'd have a little space, to 2,600. I had to make my y-axis go from like 0.001, -0.01, so I have a little space, and it doesn't look like I have a lot of space. What if I change it just a little bit? Yeah, that looks a little better. To 0.35, 0.3, or 0.35. And so it doesn't really, it doesn't look as good. So this is where we get into the idea of like, we could have drawn it without it being as accurate for people to understand. And plus it was asking for that histogram or that bar graph, not these points. All right, guys. So We have gotten to the end of part A. We're going to jump and do part B in just a little bit. So, I'll catch you guys in class. Bye.